Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking on the Hamilton's form. And to begin with, let us introduce the conjugate concept of conjugate momenta, that is the idea of generalized momenta that we have seen few slides back. So we introduce the concept of conjugate momenta. This is corresponding to the variables q, j dot, right? So this is corresponding to the coordinate velocities q, j dot. So we see that pj is partial L partial q, j dot, and from here we can find that pj dot, this is again, these two statements are equivalent, so pj dot is partial L partial qj, right? So this was our generalized momenta, this circled one, and from here we have rewritten our new variable pj dot. So now, which means that our Lagrangian typically, which was on the form of q dot comma t, can now be written, replaced with Lagrangian in the form of q comma p comma t, right? Where this p is from j, these are for all the n particles. So this p is defined from the Lagrangian in terms of q dot as follows, as this quantity hash, right? And then what we get is that what we see is that let us now look at the first equation back again. So what we have is, let us say PR is, let's say, again we are revisiting the first equation. So our first our momenta along the r direction PR was partial L partial r dot. This is with this definition here, and we see that this is mr dot, right? So L in the first example was the following here. So in this example, let us say this star. So we have differentiated now with respect to r dot. So this is from star here. So PR is this following, and then p theta is partial L partial theta, and this is m r square theta dot. We differentiate again L and we get this, and we see that r dot comes out to be, from here r dot comes out to be PR by m, and we get that theta dot comes out to be p theta by mr square, right? And so what have we got here? So then what we see is we have PR r and then the variables, PR r dot and the variables theta dot and p theta, right? And now we can try and rewrite this system of four equations in another format. Let us say we look at the first order ODEs now in terms of r theta, PR and p theta, right? And if we write down, we see that r dot is PR by m and theta dot is p theta by mr square. So these are the new variables, and PR dot is of course partial L partial r. So that is the other form of the conjugate momenta equation. if we differentiate, we will get that this is equal to p theta square by m r cube minus m capital M g by r square, and p theta dot is equal to 0. So the Hamilton's now equation. So we are almost ready now to discuss the Hamilton's equation of motion. But to do that, Hamilton's equations of motion are as follows. But now we want to introduce the concept of Hamiltonian, and of course write down the Hamilton's equation of motion. But to do that, we want to introduce some mapping, or the so-called Legendre maps or Legendre transforms, in order to eventually understand Hamilton's equation of motion. Okay, so the eventual goal is we want to find the Hamilton's equation of motion, or we want to find the Hamiltonian, right? So that is what we have, and to do that, let us shift our attention towards the Legendre transform. Okay. So the Lagrangian. So it turns out both the Lagrangian L and the Hamiltonian's H, they are related via an inversion formula. So they are related via an inversion formula. It turns out that what is this inversion formula? That is the Legendre transform, and this is what we want to see. So suppose we are given two variables v1 and v2, and we are given another two variables u1 and u2, and they are related by the formula that v1 is partial f of u1 and v2 is partial f of u2, right? So suppose these are the relationship, that is, where, so you can see that from here we can assume that this function f is a function of u1 and u2 only, right? Only two variables. So inversely I can describe u1 to be partial g partial v1 and u2 to be partial g partial v2, where my g is g of v1 comma v2, right? Inversely I can denote u and v as follows. That is another way to describe the variables under consideration. The question now is that we had to ask is, can we find this new function g? So can we find this g? So g is a function of v1, v2, right? So if f is known, can we find g? That is this question we are asking. So let us look at this question with an example. So the example that I have is, suppose I have that f is 2u1 square plus 3u1 u2 plus u2 square, and v1 is partial f partial u1, and of course v2 is partial f partial u2, and we see that this is going to be, from here we see that v1 is, u1 is minus 2v1 plus 3v2, and u2 is 3v1 minus 4v2, right? So from here we can we have evaluated these partial derivatives to find what is v1 and v2. So v1 was equal to 4u1 plus 3u2, and v2 was equal to 3u1 was equal to 3u1 plus 2u2, right? And from here I have inverted the formula for u1 and u2 in terms of v1 and v2. So now I can say that my g exists right? So G exists where G is going to be minus V1 square plus 3V1 V2 minus 2V2 square. How did we get this new function G? If we differentiate it with respect to V1, we are going to get this first expression. And if we differentiate with respect to V2, we are going to get this second expression, and that's it. So this question is how, well, this is just a hit and trial way of finding. We want to systematize this method of finding f and g. So this question is how to find, method to find f and g. Method to find f and g. So suppose my f and g they exists. My f and g exists. So I want to check what is this value. So look at this new function x. X is given by f. F was a function of u1, u2 plus g, which was a function of v1, v2 minus u1, v1 minus u2, v2. So I want to look at what is this function, right? So what do we have to check? So we have to check what exactly is this function equal to, right? So what we see is that further we can assume in this setup, we can assume that our variables v1 is partial f partial u1, and we can assume that v2 is partial f partial u2. So then what we have is, suppose we have that. Now let us differentiate x with u1. So partial x partial u1, this is partial f partial u1, right? We are differentiating everything with respect to u1 plus partial g partial u1 partial v1 partial u1. So that's the chain rule here. And then plus partial g with respect to v2 times partial v2 partial u1 minus whatever is remaining is v1 with u1 is gone plus u1 partial v1 partial u1 and plus u2 partial v2 partial u1, right? And this is well, we can club everything. So this is partial f partial u1 minus v1. So this is this minus this plus we have partial g partial v1, partial g partial v1 minus what have we got? Minus u1 times v1 u1, and then we have two more terms remaining. We have what is remaining in the next? The remaining term is partial g partial v2, partial g partial v2 minus u2 times partial v2 partial v1, right? Partial v2 partial u1, this is equal to 0, right? And now we have assumed v1 is f of u1, so this is 0. The second then we have that what we get is that since v1 and u1 are independent variables, we have that this whole quantity is 0, because partial v1 partial u1 is 0, so and partial v2 partial u1 is 0. So or I think it is easier to assume that partial g partial v1 is equal to u1. That is something we can assume, right? And so from here we can see that this quantity x with respect to u1 is 0. Similarly we can find that this quantity x with respect to u2 is 0, right? And what we see is, from here what we see is that v1 was a function of u1 itself, and f, of course, but f is also a function of u1 and u2. So essentially from here, x was originally a function of only u1 and u2 only. Why? Because v1 and v2 was completely a function of u1 and u2 via f. So now what we saw was the partial derivative of x with u1 is 0 and with u2 also is 0. Or we can say that from both the derivatives are 0 and there are only two variables in x. So x is identically 0. That is the only possibility. Which means that now we are left with an expression which is going to give us the Legendre transform. So what is the Legendre transform here? The transform is is as follows, that suppose you are given f of u1 and u2, you want to find what is g of v1 and v2, then this is also equal to this equality, f plus g is equal to u1 v1 plus u2 v2. That is satisfied. That is satisfied. Okay, so what we have is, hence what we get is that it means that we can always find g of v1 comma v2 as a function of f itself. So g can be perfectly found through f via this so-called Legendre transform. So if we know f, we can find g with this simple transformation. So again, if we go back, look at the example that we discussed few minutes back, we saw that f, so this was again the example number 1 we saw. So f was given to be 2u1 square plus 3u1 u2 plus u2 square. So now the question is, what is g here? So now g will be equal to f minus, it will be equal to u1 v1 plus u2 v2 minus f, right? And g itself is a function of v1 and v2. So we need to write everything in the as a form of v1 and v2, right? So we need to write u1 as a function of v1 and v2, and u2 as a function of v1 and v2, and of course f of u1 and u2 also has to be written as a function of v1 and v2. But here we can assume, see, in Legendre transform we can assume that v1 is partial f partial u1 and v2 is partial f partial u2, and we see that this is also 4u1 plus 3u2, and this is 3u1 plus 2u2, right? And from here we can evaluate all these values v1 v2. We see that this is also equal to so what did we get here? So we plug in these values of v1 and v2. We want to find g as a function of v1 v2. So we have to first find what is u1 and u2 in terms of v1 v2. So we invert this relationship. We invert and we find that u1 is minus 2v1 plus 3v2 and u2 is 3v1 minus 4v2, and we plug it everything here in these expressions, and we get that this is going to be our after plugging in the values of u1 and u2, we will get purely an expression of v1 and v2. We get that this is minus v1 square plus 3v1 v2 minus 2v2 square, right? And that is what we have. Okay, so then we want to continue our discussion on Legendre transform. So we want to introduce one more concept before we come to the point of Hamiltonian. The second concept in Legendre transform we want to talk about in this module is the concept of active and passive variables. So what is active variables? So suppose active and passive variables. Active and passive variables. So suppose u is a function of u1 and u is this vector u1 v1 and v is v1 v2, right? So these are, let's say, these are my active variables. These are my active variables, right? Which are transformed. So which are transformed. These are my active variables which are transformed, and the additional variables are not. We could always have more than something more than these active variables in the relation. Let's say passive variables, right? So we could have, let's say, additional variables. We could have additional variables which are not part of the transformation. Not part of transformation. Okay. We call these variables as passive variables. Okay. Okay. So in Hamilton's formulation, let us now let us quickly revisit the Hamilton's case. So in Hamilton's formulation, we had the following relation. What was that? So Pj was partial L partial Qj dot, and Qj, well, we keep this relation as it is, or we have that P and Q dot, they are active variables. They are active variables because they are related to each other via this transformation. Pj is L of Qj. J is from 0 to 1 to n, right? And then we can, so it turns out that besides this P and Q, we could have a third variable which is Q. Besides P and Q dot, we could have a third variable which is Q, and Q is the passive variable. Q is the passive variable which is not appearing in this transformation. Pj is L of Qj, right? So what we have is, suppose that f is f of, now I'm coming back to our discussion on the Legendre transform. So suppose f is a function of u1, u2 and w, and g is g of v1, v2 and w, right? So these are my Legendre transform. These are my Legendre transforms. Now clearly I am going to denote u1, v1, u2, v2 are my active variables, and my variables w here as passive variables, right? So so what I have is that f of, well, the Legendre transform says f of u plus g of v, vector v, is equal to u1 v1 plus u2 v2, right? Or in other words, we have also further assumed in this setup that v, the vector v, is the derivative of f with respect to u. Okay. So I'm writing this everything in the vector notation. So v is gradient of u, and we have that u, of course, is the gradient of g with respect to the variable v. That is what we have. So then this question now arises: what exactly is the derivative of this Legendre transform with respect to the passive variable? Derivative with respect to w, the passive variable w. So this question arises how to find that. So let us differentiate this Legendre transform. So what is it? So we see that partial f partial w plus partial g partial v1 times partial v1 partial w plus partial g partial v2 partial v2 partial w. So we are now differentiating everything with respect to w, plus partial g partial w. Now this is equal to the right hand side, u1 partial v1 partial w plus u2 partial v2 partial w, right? So if we do that and then we club everything on the left hand side, we get that this is partial f partial w plus partial g partial w. This is also equal to u1 minus partial g partial v1 partial, well, we are clubbing everything. Partial f partial w is here and partial g partial w is here. So that is what we have written here. And then this is this plus u2 minus partial g partial v2 times partial u2 partial w. So this is going to be this. Okay. So here, of course, with the active variable transformation, we know that u1 is partial g partial v1, so this is 0, and u2 is partial g partial g2, partial g partial v2, so this is also 0. So finally, we get that partial f partial w is plus partial g partial w is 0. So in other words, what we get is that suppose we have a passive variable, then the derivative of one function with respect to the passive variable is negative of the derivative of the second variable with respect to the passive variable, right? So now let us combine everything. Let us combine all these statements in the more vectorial notation to wrap up the discussion on Legendre transform. So combine all results. So what we have, this is for general case. This is for general case. So we see that for Legendre transform, suppose V is given by V1, V2, Vn are functions of active variables. These are functions of active variables, and U, which is U1, U2, Un, these are both my active variables, and W, which is given by W1, W2, Wn, these are my passive variables. These are my passive variables. Okay, so then what we get is that so we have that U is grad of F, right? So U is well, we are going to write it in the general form. So V is grad of U of F. F of U comma W. W is a passive variable here, right? So this is grad U of F, and we have that U is the grad V of G of U comma W, right? And we see that from here the Legendre transform can be written as G of U comma W can be written as U dot V minus F of U comma W. So this is my Legendre transform. Remember that this transform can be written in a simpler way. If we go back previous slide, the transform was U1 V1 plus U2 V2. So this is the dot product of the two vectors, right? So we have written in terms of the dot product here, U dot V. So this is my all the results, and finally we get the final result that the grad of W, the passive variable of F, is minus grad W with G, and we get that these two are equal and with a minus sign, and this is what we have, right? Okay, so F and G are the following. Okay, so we conclude our discussion by saying that F and G, they have a symmetric relationship and they are the Legendre transform of each other. And now in the next module, we are going to relate this F and G with our variables P and Q and describe this Legendre transform and connect it with our Hamilton's principle. So thank you so far for listening.